So that's not bad. Give you guys a little bit of break for a few days. All right, so we learned a little bit about. Has anybody tried the image segmentation?
It worked really cool.
Okay, that's what I like to hear. You learn something useful, and it actually works. You know, that's like wonderful. Okay, so let me go back. We're going to be covering something on the book. So if you want to look at the book that I have, it's chapter 9.8 and 9.9 today, which is we're going to be covering Em4 System Identification. Okay, so let's see what is that. Remember that we were doing Kalman filter, and we said there's some hidden state X that's influencing our measurement Y. And states change based on some dynamics. And we've measured behavior or data, and we want to estimate the variable X. And so we wrote down some equations. And we said X of n plus 1 depends on X of n. And there's some input to the system, maybe U of n. And there's some noise, epsilon x, where epsilon x was normal with variance q. And then we had measurement, y of n, which was dependent on x of n, plus some other noise, epsilon y. Normal, 0, and r. And we made the assumption that we know the parameters of the system. So we know A and B and C, and we know the initial state, and we know our uncertainty when we start, and we have the variances of the noise Q and R. And then given those things, we could estimate X from our measurement Y. So we found that, you know, we have some posterior, X of n given n was our prior plus this common gain times what we had observed minus what we had predicted, which is C X of n minus 1. This was our prediction. So this was our Kalman filter. Now, today we're going to ask the question, what if you didn't know A, B, and C? What if you didn't know Q and R? What if you didn't know the parameters of your model? So not only you don't know the state X, you don't even know the parameters of that system. So this is called system identification. And people, you know, take whole courses on system identification. But I'm going to teach you today how to use EM. So instead of taking a whole course, you just take one lecture. And we're going to see how to do it using the probabilistic tools that we've been learning. Okay? So what do we do in EM? What we do is that we say on the first attempt, our E step, we're going to imagine that we have the parameters of the system. We have the things that one of the things that you're looking for, the parameters, A, B, C, and things like that. And so if you had A, B, C, and the parameters of the system, what would be the best estimate of what remains, which is X? What would be the best estimate of X if you had A, B, and C? You have to answer that question. So here's the problem. I've given you some data. Why? Right? You have some data. And you want to estimate X. Well, in EM, what we do is that we say, let's suppose we have also the parameters of the system, A, B, C, the noises. Suppose you have those. So how do you estimate X, given the Y's that I gave you? Using the Kalman filter. Yes, that's right. So that's the first step of EM. We begin with assuming that we know the parameters. Okay? If we know the parameters, then we can use the Kalman filter to estimate x. That's what you guys learned at the beginning of the semester. Okay, now that you have x, what EM does is says, okay, you have this hidden state x. Now go back and estimate the parameters. A, B, C, things like that. And so today we're going to learn how to do that. How do we go from our estimate of x and do our estimate of the parameters. So what are the parameters of our system here? Well, it's the matrix A, matrix B, matrix C, variance Q, variance R, and our initial state and our initial uncertainty. X0, 0, and P, the variance of x at that initial state. Okay, so those are the parameters. So do you have any questions before I get started? What are we going to do? All right. So let's begin. Oh, you fixed it? Okay. Great. Thank you. All right, so what's going to be our E step? We have some guess. Given theta, we find x. So that's the Kalman filter. The M step is given x, find theta. I'm going to use its maximum likelihood. And so when we have a maximum likelihood problem, we always have to describe, well, what do you mean by the likelihood? What is the likelihood that you're trying to maximize? And just to be clear, after I do the M step, you go back up and then you redo the E step, right? So you iterate until the thing converges. Okay, so look at these equations here. If you had x and y, can you find A, B, C, Q, and R? That's the problem. So you have a whole bunch of data. Datas are y's. Y of 1 through y of capital N. You say, let's just take a wild guess about ABC. You just have to have the right dimensions. Using that ABC, you use the Kalman filter, you estimate x. Now you have x and y. Now you say, how do I find the best ABC for this x and y? So the likelihood that you're trying to maximize is the probability of all your x's, all your y's, given theta and u. So that's the likelihood that you want to maximize, and this is called a complete log. If you take a log of it, likelihood. So our problem today is the M step. The E step, you know how to do. That's the first half of the course. You know how to do the Kalman filter. The M step is what we're going to be focusing on today, which is basically to write the complete log likelihood of our problem, then show you how do you find the parameters that maximize that likelihood. All right, so let's start easy. Let's suppose we only had one data point. So we have some initial state x. We have that state becomes x1. We make a measurement y1, and we have some parameters, and we gave some input u1 to the system. So this is what we call our complete log likelihood. It has the states, it has the measurement, It has my parameters and it has my input u to it. So what I want to do is to write for you what the complete log likelihood is going to be. And then what we'll do is that we'll find the derivative of that with respect to the parameters that we're interested in. And that'll show us how to maximize, our complete log likelihood. And that'll be the solution to the M step. And we'll see that the M step, of course, is going to depend on X and Y. So what was your best estimate of X? What is your measurement of Y? And by maximizing the current estimate of, based on the current estimate of X, finding theta, we get our M step. And then we go back and we do the E step. Okay, so let's write down what this is. So suppose we only have one measurement Y. Therefore, we've had our initial state, x0, that changed to x1 because of the command u1 that we gave, and we made a measurement y1. And we have already made an assumption about, some theta. So we had some theta, and this produced our data. So what is this? Well, I'm going to, let's divide up our joint probabilities. So that's P of y1 given x0 and x1 times what? What goes here?
P of x0 and x1 given theta.
Thank you. Okay. Actually, let me just make sure. Let me look at my nomenclature here. This is U0. Okay. So let's look at this equation here. P of y1 given x0, x1, theta, and u0. Well, does y1 depend on x0? Does it? No, it only depends on x1. So I can get rid of x0. Okay, now we're going to split this guy. So now I'm going to have P of x1 given x0, theta, and u0. And what goes here? So look, I took this joint probability, I'm writing it as a conditional probability times what? Okay, very good. So look, I took my first measurement and I wrote it as a multiplication of three probability distributions. So this probability distribution, what is it? What's P of y1 given x1, theta, and u0? What's this guy? So here's our equation, right? So what is P of y1 given x1? What is it?
Is it just C times x1?
That's not a probability distribution. So it's a normal distribution with mean C of x1 with variance what? Right. What about this one? What's P of x1 given x0? It's a normal. What's its mean? AX0 plus BU0. What's its variance? Q. Very good. All right, last one. What's P of x0? Excellent. It's our prior, right? It's our initial state. That's going to be x of 0 given 0 with uncertainty P of 0 given 0. Does that make sense? Okay, that's if we had if we just had one data point, y1. All right, what if you have two data points? So P of x0, x1, x2, y1, y2, given our parameters theta, input u0, input u1. All right. So we're going to write. So this is the complete likelihood if we had two data points, y1 and y2. So we're going to do the same to it. So we're going to split this into a bunch of conditional probabilities where we only have one variable that's of interest to us. So let's begin with the y's. So P of the joint probability, y1 and y2. So these variables, so I took a joint probability, so I took this joint probability, we're going to write it as a conditional. So the probability of this is going to be conditioned on x. To save some space, I'm going to write it like this, going from 0 to 2, theta, and u going from 0 to 1. So this is the conditional probability times the probability, the prior probability of the x's. Probability of x 0 to 2 given theta and u 0 to 1. Does that make sense? Okay, this is exactly what we had done above, just a little bit more variables. Okay, so now let's split this up. So we're going to begin with P of y2 given y1 x 0 2 theta u 0 to 1 times the probability of y1 given okay, that's the first term times the rest of this equation I'm going to write in the line below. Second line is the second term here. X going from 0 to 2. So let's start with x2. Given x going from 0 to 1 theta u 0 to 1 times p of x 0 to 1 theta u 0 to 1. So what I mean by this, just to be clear, that's what I mean when I write in brackets. Okay, so when we look at this equation, p of y2 given y1, x, and so forth, well, p of y2, it only depends on x2. It doesn't depend on y1 and all these other x's. P of y1, it only depends on x1. P of x2, it only depends on x1, and so forth. So this last term we can split as well. So this becomes p of x1 given x0 theta u 0 to 1 times p of x0 given theta u 0 to 1. So this equation here, this probability distribution then can be written as p of y2, the first term, given x2 and theta. This is this first term. All the useful things that are come out of here are x2 and theta, times p of y1 given x1 and theta. Then this term here, p of x2 given x1 theta and u1. And then this term here, p of x1 given x0 theta and u0. Finally, last term times p of x0 given theta. So the complete likelihood is p of your hidden variable x going from 0 to n, your measurement y going from 1 to n, given parameter theta, and the inputs you gave, u, going from 0 to n minus 1. This is what we call a complete likelihood. This is what we want to maximize. We want to find the theta that maximizes this. What we've found is that we can write this as the following. Multiplication, this term here that I have above from above, from n is equal to 1 to n, p of y of n given x of n theta. Second term, p of x of n given x of n minus 1 and theta. Sorry, I forgot the u here. So multiply these guys times my prior probability of at the initial state. So we want to find theta that maximizes the expected value of the log of the complete likelihood. If we can do that, then we've completed the M step. Okay, so the basic idea here is that you have a number, the complete log likelihood. It tells you how good is your theta, the parameter that you've estimated for your system. And so, you know, if you use MATLAB or any other search mechanism, you have a number that you could give it. So if your equations are complicated and you can't find the analytical solution for it, well, you have a cost function that you could use to say, search the space, find the best parameter. Now, the problem that we have is easier than that. We can find analytic solutions to it. And so that's what we're going to do today. We're going to find the derivative of the complete likelihood with respect to the parameters that we're interested in, and that'll be the solution that we're looking for. But in reality, when you apply this to real-world problems, you know, your problems may be more complicated than what I'm showing you. It may not be these kinds of linear systems that I'm showing you. In that case, you still use the same thing. You still use the complete likelihood. You still have to compute the complete log likelihood, like I've shown you, but you can search it using, you know, any computer optimization-based process. Okay? So that's, you go from a Kalman filter to complete log likelihood, find the parameter that maximizes the complete log likelihood, then you go back and say, okay, these are the best parameters for the x's that you gave me. Let's now find the best x again using the Kalman filter, and then you iterate back and forth. Any questions so far? All right. So let's write down some of these things that we've been describing. So this probability here. So probability of y of n given x of n and theta. So this is a normal with mean c of x of n and variance r. And so what is that? That's 2 pi. We need to know what the size of x is. So suppose that x is a p by 1 vector. Oh, sorry, q by 1. In your notes, this is a q by 1, and this is a p by 1. Okay, so we're talking about probability of y. So y is going to be a p by 1 vector. So if I want to write the normal distribution for y, then I'm going to have 2 pi raised to the power of minus p over 2 times the determinant of the variance covariance matrix R raised to the power of minus 1/2 times the exponential of minus 1/2 y of n minus the mean cx of n transpose r minus 1 times y minus cx of n, close the exponential. That's going to be my normal distribution. So what about p of x of n given x of n minus 1, u of n minus 1, and theta? So the second term here. What is this? So that's a normal with mean A x of n minus 1 plus b u of n minus 1 with variance of q, which is equal to, it's going to be a normal distribution, so we have 2 pi minus q over 2 times the determinant of the matrix that's a variance covariance, in this case q raised to the power of minus 1/2 times an exponential minus 1/2 x of n, the variable that's a random variable, minus the mean, a x of n minus 1 minus b u of n minus 1 transpose times q minus 1 times this quantity. And then close the exponential. Right, so that's two normal distributions in terms of the variables that we don't have. So basically all these variables we have to find. We have to find the q, we have to find a, we have to find b, we have to find r, we have to find c. These are things we don't know. And we have a cost function. Here it is, the log likelihood. The log of this likelihood is going to be what we're trying to maximize. So we're going to find the log of this expression, find the derivative of the log with respect to the parameters that we're looking for, and then ask, well, can you find those parameters that maximize the expected value of this quantity? Okay, so the log of the complete likelihood. Well, the log of a multiplication is a sum, so I'm going to have sum of n is equal to 1 to n log of the probability of y of n given x of n and theta plus the log of the probability of x of n given x of n minus 1 u of n minus 1 and theta plus the log of the prior distribution of my prior. Okay, so I had written the expression for this. This is that normal distribution. This is another normal distribution, and this is a third normal distribution. So we're going to find logs of those normal distributions. So this is equal to sum all right, so log of this first term, p of y, log of this quantity here. It's going to have some constant terms in the front. It's going to have log of this determinant and then log of this exponential. So let's begin with the log of the exponential. Minus 1/2 y of n minus c, the mean x of n, transpose r minus 1 y of n minus c x of n. So that's the exponential. We took a log of it, we just got the exponential. Then we have terms in the front, minus 1/2 log of the determinant, and then some constants. So that's the first term, p of y, given x of n. We found the log of it, we're going to have a sum. Then the second term, p of x given x minus 1. So it's going to be another minus 1/2 x of n minus ax minus 1 minus b u of n minus 1 transpose q minus 1 times itself. some constants at the end. Okay, so that's our these two terms here. Then I'm going to have a third term plus, minus 1/2 log of this, which is x of 0 minus my prior, x of 0 given 0, transpose, times my prior uncertainty So we can write the log of the complete likelihood. And our final step is take derivatives of this with respect to our unknowns. Any questions so far? All right, so just to remind you, what are we doing? Let's go back. Go back to the beginning. So we have a system that's generated data for us. We've measured y of n. And if we knew A, B, C, the noises in our system, then from y of n we could estimate x of n using the Kalman filter. Well, we don't know x of n. And we don't know A, B, C. So we can't just start using the Kalman filter. What EM does is says, make a guess about your parameters, theta. These are the parameters of my system that I don't know. Make a guess. Start with some guess. Given that guess, you can find, using the Kalman filter, the values x. Okay, now that you have x, go and find theta. And what we mean by that is that find a theta that maximizes what we call the complete log likelihood. The likelihood of the things that you know, x and y, given the parameters and the input u that you gave. So we want to find theta that maximizes the complete likelihood. If we could do that, then we will have completed the M step. And by completing the M step, we now have a new set of thetas, and then we go back and we re-estimate x's. All right. So we're going to have to find derivative of this with respect to some complicated things, matrices and so forth. And okay, so how do we do it? So let's just write down now our E and the M step. Okay, sorry. So what was our E step? Was to find x of n that maximizes the expected value of x of n given y 1 to n and u 0 to n minus 1 and theta, which was the Kalman estimate. So the x's that we're going to assign are going to be the expected value that we get from the Kalman estimate. Our M step, we fix x from 1 to n. We find theta that maximizes the expected value of x and y given theta and u, the complete log likelihood. Okay, so what we need to do is find theta that maximizes this quantity. So I'm going to do it for a couple of the variables. So start with the variable c, this matrix C. We want to find this matrix C. So we're going to find the derivative of our complete log likelihood with respect to the matrix C. That's what we're interested in. So the part of the problem that we want to work on, the likelihood, that we want to work on is the part that has a C in it, which is that first part. So the part that has C in it, the part that we want to find derivatives, is this first part here. So all I did is that I just multiplied this through. Okay, so I need to show you how to take derivatives of this with respect to this matrix. So this is a scalar quantity, right? The likelihood is just a number. And so I can write this in terms of the transpose of this. So this is the same as minus 2 y of n transpose r minus 1 c x of n. Same as this. So this is just a vector here. Call it A transpose times C. It's another vector. Call it B. So this is A transpose CB, some scalar quantity. So we want to know how to take a derivative of that with respect to C. So we can use an identity. Derivative of A transpose matrix X times B with respect to X is, of course, going to be a matrix. And in this case, it is A times B transpose. So then the derivative of this structure, derivative of my likelihood with respect to the matrix C, is going to be a sum minus 1/2 is going to take care of the 2 here. And this term, using this identity, I'm going to get r minus 1 times y of n times x of n transpose. Right? A, which is r minus 1 times y of n times b transpose, x of n transpose. In the second term, is going to be this quadratic function, and in that case we have c times x of n transpose. And let's just look at the dimensions to see if this makes sense. So R was the covariance of the y equation, and that's going to be a matrix of p by p. Y is a p by 1. X is a 1 by, xn transpose is a 1 by q. So this term is going to be a p by q. And here we have C, which is oh, I forgot an R here. Yeah, sorry. Very important. Yeah, otherwise R's won't cancel out. Okay, so that's going to be our derivative with respect to C. We set that equal to 0. And of course, we get the following: r minus 1 times the sum of y of n xn transpose minus c xn transpose, that's equal to 0. And so we get the following equation. We get c times the sum of x of n xn transpose n is equal to 1 to n is equal to the sum n is equal to 1 to n y of n xn transpose. Okay, so what we're supposed to do is to find the matrix C that maximizes the expected value of the likelihood. And so when we take the expected value of this, we have to replace these x's with things that are going to take into account the expected value of it. So let's see how we're going to do that. So we have the uncertainty of x, which we write as p of n. And so p of n is the expected value of x of n xn transpose minus the expected value of x of n times the expected value of x of n transpose. So that's the definition of variance. And so this term here, c times the sum, we can replace x of n, the expected value of this term, this expected value is p of n plus this. And that's equal to the sum of n is equal to 1 to n y of n times the expected value of x of n transpose. And so our matrix that we're looking for, C, is going to be the sum of p of n plus the expected value of x of n transpose times no, sorry. No. Do this again. I inverted the wrong sum. All right, so that's the right side. This is why, see, by actually doing these equations, I learned to be much more appreciative of the mistakes that you guys are going to make during your DBOs. All right. Okay? So there are four more terms in our unknowns, but they're all very similar. You just find derivatives of the likelihood with respect to those. And you have it in the textbook. I've done it in there for you. Do you see what's going on? Do you see the procedure? So we have x's, right? We have the x's that we got from the Kalman filter. We have the uncertainty that we have from the Kalman filter. We have the measurement y, and this gives us the estimate of c. That's the M step. And we do that for every variable that we don't know, and we're always going to get it in terms of the things that we do know. And that's how you proceed. All right, any questions? So that's system identification using EM. Right? We didn't know the state of the system, we didn't know the parameters of the system. We found it by maximizing the complete log likelihood. All right. Have a good weekend. I will see you next Tuesday.